Hey everyone, this is Dr. Walker. In this video, I'm going to go over the example from v034b on horizontal loops when dealing with centripetal force. This problem is called a spinning wedge. It says a toy consisting of a small frictionless wedge is spun at a constant speed when a vertical rod is rotated as shown. So we have this vertical rod being rotated, and it causes the whole wedge to rotate and the mass, this block here, to rotate as well. The mass on the wedge remains at constant height as it is spun, as the wedge is spun. So that means that as this wedge is spun, this mass is going to move in a horizontal circle. What is the speed of the mass when it sits a distance L up along the sloping side? So the first thing to do is to identify this as a centripetal force problem because we have circular motion. We know that we need to draw a free body diagram and then identify all of the forces either towards or away from the center of the circle, and then use Newton's second law for circular motion. So let's start with a free body diagram. Feel free to pause the video at any time to try these steps on your own. So the first thing, the free body diagram, we know that the object has a weight going straight down. I'll call it Fg. We know that because it's on an incline, there's also a normal force going up, perpendicular to the surface. There's no other force, there's no friction, so those are the only two forces. Now we know that we need forces towards or away from the center of the circle. We need horizontal forces. Usually when we're on an incline, we find the x and y components of the weight. But weight is vertical. It's perpendicular to the circle of motion, so it's not going to contribute to the circular motion. However, the normal force has an x and a y component. We can draw them. The x component points to the left, and the y component points upward. Now we can see that nx points towards the center of the circle, and that is the force that is causing the circular motion. Let's go ahead and set up our equation for circular motion. The sum of the forces equals mv squared over r. We have only identified one force that is pointing towards the center of the circle. That is nx. So nx is going to equal to mv squared over r. Let's write nx in terms of n and the angle theta. So we're given this angle theta for the wedge, and that angle happens to be the same angle as this angle right here. So if this is theta, then this angle here in the triangle is 90 minus theta, because this is 90. And this is 90 right here. So if this is 90 minus theta, that means that our theta is actually up here. So we're going to use this theta in the triangle to write our components. Nx is going to be opposite of theta. So it's going to use sine. We're going to write nx as n sine theta. That's going to equal to mv squared over r. Now, if we could solve for v and just write it in terms of n and r, we'd be done. But we want to write our answer in terms of the variables that we are given. We are given m, l, and theta in this problem. So let's figure out what n is. Do you have any idea how to do that? In general, what we can do is we can look at the y direction, or any direction that's in equilibrium, which happens to be the y direction in this case. And we can solve for n that way. It says that the mass remains at a constant height, so it's not jumping up and down as it's moving in a horizontal circle. So it is in equilibrium in the y direction. What we can do is we can use Newton's second law in the y direction and say we are in equilibrium. And now we sum up the forces in the y direction. We have ny going up and Fg going down. Those two forces are balancing each other. This will allow us to solve for the normal force. We can write ny in terms of the cosine of theta since it's adjacent to the angle. So ny is going to be n cosine theta. And Fg is going to be mg. Now we can solve for normal force. Normal force equals mg over cosine theta. We know that we want to plug this n into this n over here. But first, let's also, well, actually, we can do that first. So let's go ahead and plug in this n here. So we're going to have mg cosine theta over cosine theta for n. And then we're going to have sine theta equals mv squared over r. And we can see that the m's cancel out. And we can go ahead and multiply by r. So we're going to have rg sine theta over cosine theta equals v squared. Now let's get rid of the r because we want to write our answer in terms of L. R is the horizontal distance from the center to the object. So if we draw it down here, so it's easier to see, we can see that there's a relationship between r and L and theta. We know that cosine of theta is equal to r over L adjacent over hypotenuse. So r is equal to L times cosine theta. We can make that substitution for r in here as well. Let's do that. We're going to have L cosine theta times g times sine of theta over cosine of theta, and I'll just say equals. And we can see now that the cosine thetas cancel out. So we have v squared is equal to lg sine theta. So that means that we can take the square root of both sides and get v equals to the square root of lg sine theta. A very important remark is that this problem is very similar to an example called the bank curve problem. You will probably see a problem where there's a car that is going around a banked curve. So instead of the curve itself moving like in this toy, it's the car itself that is moving in a horizontal circle on a banked curve. The way to solve that problem is exactly the same way that we solved this one. The only difference is that in that problem, we don't usually write the answer in terms of L, we usually keep it in terms of R. I hope that helps. Have a great day.